to move this over? To start by thanking the organizers. I think events like these are a lot of fun, and I'm very happy to be here to talk about an area of research that is very near and dear to my own heart, which is the study of relativistic jets that emanate from supermassive black holes. And I'll end this talk with a brief discussion of the Event Horizon Telescope, which is a new array of telescopes, which is very much on the verge of making some pretty exciting discoveries. And so I think it's a pretty exciting time to be doing jet research. And just a quick note about my title, Nature's Death Stars, is very much a reference to the dreaded Death Star in Star Wars, and it's it's a planet-destroying beam. And it turns out that nature is also very efficient at creating highly collimated beams of relativistic plasma on a lot of different scales. And so today I'll be discussing some of the largest beams of relativistic plasma, or jets, that we know of in the cosmos. And these are extragalactic jets. And so I work up the street at the Max Planck Institute for Radio Astronomy, as many of my colleagues in this room do as well. And I thought I'd start with an image of the Jansky Very Large Array, which is an array of radio telescopes in the desert in New Mexico. And so this array produced the following image, which for me is sort of where my interest in jet research began. And so this is an image of a radio galaxy known as Cygnus A. It's one of the brightest radio galaxies on the sky. And so the light, the emission that we're seeing in this image is not from light that we would detect with our eyes. It's longer wavelength radio waves. And to be very clear, this bright feature in the very center of this image is not a star. It's the center of an entire galaxy. And you can see these bright relativistic jets that emanate out from this central region and move out into extragalactic space, the space between galaxies. And so this is an absolutely immense structure in the universe. And finally, these jets impact on this space between galaxies and produce these bright stationary features, which are known as hotspots. And so the emission that we're seeing is from electrons in the space between galaxies that are gyrating or spinning about magnetic field lines. And so to kind of give you a sense of the scale of this entire system is 100,000 parsecs across. And a parsec is a fundamental metric of distance in astronomy. Now, if you're not an astronomer, I want to kind of devote some time to this talk to try and conceptualize what we really mean by 100,000 parsecs. How big is this thing in space? And so to do that, I'd like to kind of play a thought experiment with you, which is we're going to kind of go Alice in Wonderland. We're going to shrink the entire universe down to sort of help us better conceive of these distances. And so to do this, I'm going to introduce a scale factor that I'm going to apply to every object in the universe. And this scale factor is going to shrink things down to smaller sizes. And so to kind of start this thought experiment, I thought I'd begin with the sun, which is a fairly intuitive place in astronomy to begin. It's a part of our everyday life. And so it turns out the sun has a radius of about 10 to the 8 meters. And so the question is, what scale factor would I need to shrink the sun down to a ball that I could hold in my own hand? So it turns out if you plug these numbers into that equation, that scale factor is about 10 to the 10. That's 10 times 10 times 10, 10 times. That's a really big number. Now, if we take this scale factor and play the same game with the Earth, which has a radius of around 10 to 6 meters, the Earth would shrink down to a size that's just a little bit smaller than the tip of a ballpoint pen. Now, the Earth-Sun distance is another fundamental metric in astrophysics. We call it an astronomical unit. It's about 150 million kilometers. That's how far we are from the sun. And so if we applied the scale factor to that distance, 150 million kilometers shrinks down to about 15 meters, which, to put into perspective, is roughly about the size of Fiddler's Pub. So if you put a ball at one end of this pub and a ballpoint pen at the other, you've got a sort of scaled-down model of the Earth-Sun system. Now, Pluto, and by the way, Pluto is absolutely a planet in my book. So this is the official line, but Pluto's still in my solar system. It turns out that Pluto's about 40 AU from the sun, 40 times the Earth-Sun distance. And so if we played the same game with this scale factor, that distance scales down to about 0.4 miles from Fiddler's Pub. And I apologize, I lived in the States for 6 years. I'm originally Canadian, so this should be in kilometers, but the Americans got to me, so I think in miles now. But Ferdinando's, which is just up the street across from the Max Planck, is where Pluto would be in this scaled-down version of the universe. And shameless plug, Ferdinando's is the best cappuccino I've had in Bonn. So if you haven't been there, I encourage you to go there. And when you're having your coffee, remember that this is where Pluto is in this scaled-down version of the universe. So now moving out to larger scales, the next closest star to our sun is Alpha Centauri, which is about 4 light years away. So if we play the same game, that distance shrinks down to about 2,700 miles from Bonn. And this is kind of fun. I Google mapped this to figure out where you could get in the world from Bonn, and it turns out this distance is roughly the distance to the pyramids of Egypt. And this is actually a really interesting fact, because you think about it, that's the next ball, the next star over. The distances between stars are really vast. All right, so this is where the next star is in this scaled down version of the universe. Now we're doing extragalactic astronomy, so we need to go to even larger scales. So we're going to move up and consider our entire Milky Way galaxy, which is the aggregate of hundreds of billions of stars all orbiting in this giant disk that we call the Milky Way. And this is, again, a separate talk, but that distance across our galaxy turns out to be roughly 25,000 parsecs across. All right? And so if we shrink this down in terms of a distance, it works out to be roughly 2,000 times the circumference of the Earth. So again, the analogy breaks down. It's just a really big number. So galaxies are really big, which brings me back to this first image of this radio galaxy, which is 100,000 parsecs across. So our entire Milky Way galaxy could very comfortably fit in the central region of this radio galaxy. So these jets are absolutely immense objects. This is incredible amounts of power that are being generated by these radio galaxies. Which begs the question, what on earth is happening in the center of that galaxy? It turns out radio galaxies are very rare. Only 10% of galaxies produce jets. So something very special is happening in the center of Cygnus A. So this has sort of been an initial look at this from the perspective of a radio astronomer. But a huge piece of the puzzle was added 10 years ago, in 2008, with the launch of the Fermi Gamma Ray Space Telescope. This is an image of the launch 10 years ago. And so this is a telescope in orbit around the Earth, and it's been observing for over 10 years. And it's a ray that detects high-energy gamma ray photons from outer space. The idea is that a gamma ray comes in and transforms into an electron and a positron, which we measure through this array. So we're able to measure the energies and the trajectories and infer from where on the sky these gamma rays originate. I think a major discovery of the last decade is that the gamma ray sky is dominated by these relativistic jets. And so this image is of the entire sky. So we have the southern hemisphere and the northern hemisphere, and this bright band across the center. I'm going to go back here, sorry. This bright band here is the Milky Way Galaxy, which is also a source of gamma rays. And that is, again, a fascinating talk, and I'm going to completely ignore that. And what I want to draw your attention to is all of these little pinpricks of light that have circles around them. Those are relativistic jets. And not only relativistic jets like that radio galaxy, but the relativistic jets that happen completely by chance to be pointed more or less directly at the Earth. And so what we're seeing is an entire view of the sky with hundreds of Death Stars with their lasers pointed directly at the Earth. Now, fortunately for us, these objects are very far away. But this is a completely new way of looking into jet research and looking at these blazars. And these jets that happen to be pointed directly at the Earth are referred to as blazars. And really another exciting aspect of this jet research is that these blazars happen to be highly variable. So they vary on time scales of months to days and even minutes. You see them flickering in the gamma ray sky. And so the idea is that the centers of these galaxies is a spinning supermassive black hole that collimates and launches a relativistic beam of plasma into extragalactic space. And some of these, by chance, happen to be pointed directly at us, producing these high-energy flares that we see in the gamma ray sky. So I think the idea here is that somehow, and again, this is a very active area of research, the supermassive black hole is the prime mover. It's the thing driving these immense energetic outflows, which begs the question, what is a black hole? So my own sort of take on this is to approach this question from the concept of escape velocity. And I love this image. This is an image of a boy running along the beach and a rocket on its way up into space. And so I think clearly the boy is not going to get off the planet, the rocket is. And so there's a very nice description from Newton's laws that describe the speed that you need to get, which is referred to as the escape speed, and what that is in terms of a planet of a given mass and a given radius. So for any planet out there in the universe, there is a set speed based on its mass and its radius that you would have to travel at to escape the gravitational pull of that planet. Now, if we simply replace this escape velocity with the speed of light, which is an absolute speed limit in the universe, you get a very nice description for the ratio of a massive black hole to the radius of a black hole. And this is what we refer to as the event horizon. So in the case of a black hole, even light becomes like the little boy on the beach. Can't get off, right? And there's a very well-defined radius for a given mass of black hole. We call this the Schwarzschild Radius. And so this service that we refer to as the event horizon is sort of this point of no return, where even light is trapped in the gravitational well of this intense celestial object. Now, the thing that's really exciting about right now, in 2018, moving into 2019, is for the first time, we have arrays of radio telescopes that are beginning to probe these sorts of scales. And so I think it's a very exciting time. We're beginning to make images down to event horizon scales. And this is a very exciting area of research. I'd like to share another aspect of this research that I really find interesting, which is that in addition to these intense gravitational fields that warp the space around black holes, there's also a very sizable effect on the passage of time. This is referred to as time dilation. And so this is an expression that basically governs how the rate the passage of time changes depending on how fast you're moving. And it turns out that as you move faster and faster towards the speed of light, time slows down. And this is very relevant in the study of these relativistic jets. When we see these flares go off with the Gamma Ray Space Telescope, what we see is a flare occurring over 20 days, might be 100 days in the frame of the jet. And so you always need to toggle back and forth between the observer's frame, where we are here on Earth with our telescopes, and what's actually happening out there in extragalactic space. So it's a very real effect. In this film, in a very real way, the entire plot of this film, Interstellar, centers around the implication of this equation and what that would mean for space travel and traveling close to the speed of light. Now, I wanted to show this image, which is kind of, I think, a nice summary of our thinking at the moment as to what actually powers these relativistic jets. It turns out there's sort of three ingredients that go into the recipe that can make a giant cosmic outflow that moves very near the speed of light. And so I guess the first thing I want to talk about is magnetic fields. And so, again, this is an active area of research, and this is by no means completely understood, but somehow we think in the jet, there's a mechanism that takes the pressure of magnetic fields that could be out there within the jet, extragalactic space, and converts that into energy within these relativistic outflows. And in fact, there's a whole vein of research called magnetic reconnection that is studying basically how nature is able to push magnetic field lines together with enough force you can actually break the magnetic fields and release immense amounts of energy. And this, again, could be powering these high energy flares that we see in the gamma rays. And somehow these magnetic fields are wound back and are connected to this central supermassive black hole. And so, we talked a little bit about the event horizon, but I wanted to highlight the fact that there's actually a second horizon, which I find really interesting. It's referred to as the static limit, the static horizon. And this is a horizon within which even space itself is getting wound up with the black hole as it spins. I, as a human being, weigh what I weigh. And if I was in a chair and spun around, nothing would happen other than the fact that I would get dizzy. But if I weighed 1 billion times the mass of the sun and I span around in my chair, I would have a very quantifiable effect on the space-time in this room and indeed this solar system. And so we think that somehow these spinning black holes are winding up these magnetic fields, these sort of helixes. It's kind of like a strand of DNA. And somehow those magnetic fields tap into the energy of this spinning black hole and power these relativistic outflows. Now, one other piece of the puzzle that goes into this is the fact that in the centers of these galaxies, these black holes are feasting on the gas in these central regions. So we refer to this as accretion in astronomy. There's huge amounts of energy that are released as this gas plunges into the event horizon of these black holes. And so, again, it's these three ingredients: the fact that the black holes are accreting gas, they're spinning, and there are magnetic fields that somehow launch these relativistic jets. Now, I like this number, which is kind of a rough parameterization of the rate at which this gas is flowing into these black holes in active galaxies. And again, this is a whole other talk of where this number comes from. But estimates for active galaxies put these kinds of rates of accretion at around 2 solar masses per year, which maybe doesn't seem that big when you consider the size of an entire galaxy. But I like to convert this number into moons per second. And so it turns out that that number works out, if you do the math, to around 2 moons per second that these galaxies, these black holes, are feeding. And these accretion rates are sustained for millions of years. And so I find that really an amazing fact when thinking about these galaxies and the jets that come from them. So I guess I'd like to just end this talk with a brief discussion of how we actually go about taking a picture of a black hole, because this is something that is very much on the forefront of research right now, up the street, literally several blocks from here. And the technique to do this is referred to as very long baseline interferometry. And so I started the talk by showing you a picture of the Socorro, the array in Socorro, New Mexico, which is an array of telescopes spread across a desert. But we can do this on a larger scale. We could spread our telescopes across a continent. And so what we do is basically create these arrays, and they form baselines between all the pairs of telescopes in your array, which are shown as these red lines. And this technique, which is referred to as aperture synthesis, makes use of the rotation of the Earth as a cog in our telescope. And so the idea is that all the telescopes look at a jet at the same time, and we let the Earth rotate. And based on that, we can fill this in and create highly resolved images of these relativistic outflows. And so this is an animation. We do this, month to month, year to year, and we build up movies of basically the evolution of this radio emission over time. As you can see the date progressing on the top of this panel. And so what we typically see in the case of these blazars, these jets that are pointed directly at us, is a bright feature that we call the radio core. And the supermassive black hole is somewhere in the center of that object. We can't really see into it. And then over time, we see blobs of plasma move at very close to the speed of light along the jet. And what's really exciting is that if we go to longer and longer baselines, now not just considering an array of telescopes across a desert or an array of telescopes across a continent, but entire arrays across the entire planet. And if we go to higher and higher energies in terms of the frequencies that we observe, we're able to peer deeper into that radio core, to the very point where, at least for a few sources, we might be able to image for the first time the event horizon of a supermassive black hole. And so the data is literally up the street from here. This is ongoing as we speak. And I encourage you to come. I think there's going to be an on-tap talk in March, and I encourage you to come to that, because I'm just showing a computer simulation. We might actually very soon have real images of black holes. And I think it's a pretty exciting time for very long baseline interferometry, for jet research, and black holes in general. So I will thank you all for paying attention, and I'll stop there and open up to questions. Thank you.